Okay, so what we'd like to do now is let's keep to d is equal to 2. So we're still going to be in d is equal to 2, but we now want to take a look at Minkowski space-time. And let's write down the conformal killing vector equation, and we'll also write down the solutions to this equation. So there's the conformal killing equation written at the top. What do we need? We need the metric. So eta alpha beta is equal to. Now here you've got some choices. You're going to take the mostly minus or mostly plus. I'm going to choose minus 1, 1 metric. So this is opposite to what we were using when we talked about the Poincare group, but that's fine. You should be able to work with either convention. So if you don't like this choice, you make a different choice and you work out. So I suggest you can redo with the opposite convention. Okay, that's very easy to do. Okay, now let's actually take the killing vector equation. So there it is. We again got d is equal to 2, so the 2 will cancel with d. And let's just write down what this equation is. So if we choose alpha is equal to beta is equal to 1, then it's quite clear that the right-hand side becomes 2 d1 d1. So we get 2 d1 d1 is equal to, the 2 over the d will cancel, and we've got a d dot zeta. So let's just write down what is d dot zeta. So this, as usual, will be d naught zeta naught plus d1 zeta 1. And then if you use the metric to raise and lower indices, we know dropping the naught will cost us a minus with the metric above, and dropping the 1 doesn't cost us a minus. So that's the divergence. So we've got minus d naught zeta naught plus d1 zeta 1. And then we've got eta 1, 1, the eta alpha beta. But eta 1, 1 is just 1. Okay, I'm going to remove this divergence. We now know what the divergence is, so we don't need it. So that is the conformal killing vector equation in Minkowski space. At least the alpha is equal to beta is equal to 1 component of this equation. You'll get the same equation. So you'll get the same equation for alpha is equal to beta is equal to naught. You'll get exactly the same equation. Now let's take a look at alpha is equal to naught and beta is equal to 1. In this situation, we get d naught zeta 1 plus d1 zeta naught. So I've just plugged in the alpha and the beta onto the left-hand side. Then on the right-hand side, we've got an eta naught 1. That's an off-diagonal component of the metric. It vanishes. So that's what the conformal killing equation looks like. So let me just box these two equations, and I will give them both numbers. So let's call this equation number 1. And I'll just make a note. You get the same equation for alpha is equal to 1 and beta is equal to 0. And then instead of using this, the upper boxed green equation, let me just simplify this a little bit. I'll put all of the terms on one side. So bringing across d naught zeta naught, it changes sign. So we've got d naught zeta naught. And then we would have plus 2 d1 zeta 1. But we've got a d1 zeta 1 that when we bring across, it becomes negative. So we just get d1 zeta 1 is equal to 0. And that's the second equation. Okay. So this is second equation number 2. And this equation, those two are the same. Good. Okay, so now let's take a look at 1 and 2. Okay, so first of all, from equation 2, well, if we take in fact, let me write it like this. From the derivative with respect to 1 of equation 2, what do we get? So if we take a derivative to 1 of equation 2, we get d1 zeta naught plus d1 squared zeta 1 is equal to 0. And then from d naught of equation 1, so d naught on equation 1, we get, oh, sorry, this is d1 d naught. Did I do that right? Yeah. Now, d naught on equation 1 tells us that d naught squared zeta 1 plus d1 d naught zeta naught is equal to naught. Now what you can see is this term appears in both equations, so we can eliminate it. And if we eliminate that from these two equations, then these two equations become a single equation. Let's write it as d naught squared minus d1 squared on zeta 1 is equal to naught. And this equation we recognize, this is nothing but the massless wave equation. And similarly, we could have chosen to take the naught derivative of 2 and the 1 derivative of 1. So let's just say from d naught of 2 and d1 of 1, we would get the following equation. D naught squared minus d1 squared on zeta naught is equal to naught. So let's just box these two in red. So what have we learned? Zeta 1 and zeta naught in this Minkowski space both satisfy the massless wave equation. Now we want to solve the massless wave equation. Well, there's a little trick to do this that I'm sure that you know. So let's say to solve the two boxed red equations, use a new set of coordinates, x plus minus, and this is nothing but x naught plus or minus x1, and of course this would be t plus or minus x. These are called light cone coordinates, and the big advantage of light cone coordinates is that if you write the massless wave equation in these coordinates, it takes a particularly simple form. So I'm going to ask you just to verify this, but I'm going to tell you in these coordinates, so you're just changing coordinates, no big deal. So go ahead, make sure you can do that. But in these coordinates, this is what the wave equation becomes. D plus D minus on zeta naught is equal to naught, and this is equal to D plus D minus on zeta 1. What's the big advantage? It's now trivial to write a solution. So trivial to solve. So what is the solution? For example, let's write the solution for zeta 1. Zeta 1 is given by any function of x plus any function of x minus. So this should be completely clear to you, but let's discuss it a little. If we take d minus of zeta 1, then d minus will actually kill f completely. We'll land up with d minus of g. If we now take a d plus on d minus of zeta 1, we get 0 because d minus g is also a function only of x minus. So it's only a function of x minus. It's annihilated by d plus. if you'd chosen to take the plus derivative first of zeta 1, then all that would have survived was d plus acting on f, and then you would have found that d minus d plus on zeta 1 was 0. So this is why changing to these light cone coordinates is so nice. It's really trivial to solve the massless wave equation. Okay, we don't need this anymore. Let's remove it. Now, be careful. You might think it's equally trivial to write a solution for zeta naught, but for zeta naught, be careful because we have to take into account equations 1 and 2. So let's say, what does equation, well, let's choose one of them. Let's look at equation 1, okay? You can use either one of them. I'll use equation 1. You can check that with equation 2. You still get the same answer. So let's just rescue this equation down the bottom here. So this is the equation that we want to use. And what is this telling us? Well, it's telling us the following. Let's leave that in black. This is telling us the following. This must have been from a previous lecture. Okay. So what we now know is d1 on zeta naught must give us exactly the same thing as minus d naught on zeta 1. Now, if we think about the f of x plus, this is the f of x naught plus x1, and for g, it is x naught minus x1. So if we take, if we want the 1 derivative of zeta naught to be equal to minus the naught derivative of zeta 1, then what should zeta naught be? Well, zeta naught should be equal to, so we'll again have f of x plus, and we will have g of x minus. If we take a time derivative of zeta 1, time and space derivatives of f are exactly the same sign. So over here, we'll need to have a minus to swap the sign of the derivative. But for g, the time and space derivatives of g have a different sign because it depends only on x minus. So here we must have a plus. So zeta naught depends on the same two functions, f and g, just that it is an opposite sign. So let's maybe box these last two equations. These are the killing vector, the conformal killing vectors. And let's just write down maybe one more thing. So if we look at zeta naught, let's maybe put it over here. So we can write zeta naught as follows. It's minus a sum over n, let's call the Cn1 x plus, which is x naught plus x1 to the power of n, plus, and for g, let's write sum over n Cn2, and we've got x naught minus x1 to the n. And then if we look at zeta 1 is the same thing, but with pluses. Now, the reason why I wanted to write this down is that once again, what you can see very clearly is that Cn2 x naught minus x1 to the n. There are again an infinite number of parameters. So our parameters would be the Cn1s and the Cn2s, which means there's an infinite number of conformal transformations. They're again specified by two functions, f of x plus and g of x minus. When we were studying in Euclidean space, our conformal transformations were specified by f of z and f bar of z. So that again was two functions. So this is a nice matching between the two. Now, I'm going to suggest to you that you take this analysis a little further. I'm not going to do it, but you should do it. What you should do now is work out the elements of the Lie algebra. You can do this both in Minkowski space and in Euclidean space. Once you've got the elements of the Lie algebra, work out their commutators. And well, then you would have specified what is the Lie algebra for the conformal group. We're not going to go through this exercise in D is equal to 2, so you should do it. But when we study conformal transformations in D greater than 2, we will calculate the elements of the Lie algebra, and then we will calculate their commutators.